Hi folks, welcome back. Hopefully you've seen the first little video on normal distribution. We just kind of basic explanation that the area under the bell curve, it was equivalent to 1 in total, and we use a table in association with half the curve, and basically so how did we calculate the z-scores, how did we get the value from the tables, and how did we use it in the problem. Okay, so we're just going to go for another example here. So we're just saying 1,000 teenagers, and it's saying that their mean height is about 1.7 meters and a standard distribution of 0.1 meters. So if we go 0.1 either side of the mean, that's between 1.6 meters and 1.8 meters. What we're saying here is 2/3 or 68% of these teenagers lie within that range. Okay, so there's information, and here's the question. How many are over 1.83 meters? So we'll get three highlighted values here: the mean, standard deviation, and our height. That's what will become our x value. Okay, but how many are over? How many are taller than 1.83 meters? So that's important. So there, I've just listed those three values there, and just get a little illustration with the bell curve, the normal curve. There's the mean in the middle, up to 1.83. Okay, to the right of the mean, and we're asking how many are over 1.8. So we're going to the right here. So I've highlighted that. That's the area. And like we're saying, that's a probability of interest. Okay. Right. But when we go to the tables, it would give you the probability going from 1.7 up to 1.83. So we'll need to think about that. So what we're going to do is we're going to normalize the curve here, and we're going to change the 1.7 in the normal process to make that mean 0. And then we'll normalize the 1.83, and that's where we get the z-score. Okay, right, here's the z-score. And that's one little formula here for the z-score, involving our three values of x, mean, and sigma. Okay, so just pop them in there, sort out the top, 0.13 divided by 0.1, and our z-score is 1.3. Okay, so this is where we go and get our tables that start off at 0. So we're going up to 1.3. So probably we're only going to one decimal place here. So we're actually just going to be looking at the left-hand column directly under Z. Okay, so so there would be your table there, and you can see that's quite long. So there's your entire table. It only goes up to about 3.6. Okay, that's fine. So I'm just going to magnify that a little bit, and so as long as I go down to include maybe 1.3, and I think I can see it a little better there. So 1.3, so we're only going to one decimal place there. So I've highlighted that there. But so after the 3 would actually be a 0. So I'm going to go up to 0.00 and bring a column down there. So the intersection of the row and the column, that's our area, which is our probability. So I can see that as 0.4032, and so that means the area probability that we got when we put in 1.3 is 0.4032. Okay, so our probability area is 0.4032. Yeah, probability. Okay. Here we're going back to the scenario there. Yeah, you've got your mean, standard deviation, and your x value, but we've standardized those So that's 0.4032. That probability is actually there, okay? Because that's what the table actually gives you. So I'm declaring that, naming that as P1, because we're going to have to include another probability, the actual probability we're looking for. So this is a probability from the table, okay? Because it always comes away from the mean, which starts at 0. So that is what the table, and just going back to the table there, you can see I've just highlighted that there. So it's starting at 0, okay? And as we go down here, you can see that gives you the first decimal place, and up the top there, that gives you the second decimal place. But as you come away, you can see the values, the areas are getting bigger and bigger and bigger. But just to specify or clarify, they are coming away from the mean, that little arrow in blue. So that's our value probability we're getting. That's not the one we want. Okay, right, there's P1 from the table. That's the one we want. So that relates to heights over 1.83 meters. So hopefully I've got enough information to calculate that probability. Well, here we go. We've seen previously that half the curve, because the total probability is 1 under the curve, okay, we've got half the curve, so that must sum up to give you 0.5, because the other half, yeah, half and half is 1. So, but we're on the right hand side, and it looks like those two probabilities give us a half. That's the statement I'm making there. So the sum of those two probabilities gives me 0.5. So it looks as if I've got enough information here to go and calculate, well, I refer to that as P2. Yep, that's the one I'm interested in, that probability. So there's a relationship, P1 and P2, 0.5. What do we know? Well, what is P2? That's what we're trying to find, that heights are greater than 1.83. So what is P1? Well, that's actually the heights coming away from the mean 1.7 all the way up to 1.83. Okay, don't worry too much that I don't have a less than or equal to in the 1.83, because the majority of the time you can't pin it down. So you can go away and have a little discussion with people. I'm happy with that. You can put it in if you want. Right, okay. We calculated that, we got it from the table. Okay, that's for 0.4032. Right. I've isolated P2 because that's what I'm looking for, so it must be a half. Take away P1, which we know is 0.4032. Calculator time, put that in the calculator. So our value of P2 is 0.0968. Okay. So that means the probabilities of our heights greater than 1.83 is exactly that. Okay. And I'm happy with that. Sometimes if you just want to convey a value, some people like to have it converted into a percentage. So 9.68%, around about 10%, a tenth. Okay, but we've not finished with the problem there, because we wanted to know what was the probability of people having the height greater than 1.83. Okay, so can we find out the number of teenagers who are bigger than 1.83 meters? Well, if I just take that probability that I've found there in conjunction with the total, because the total was 1000, so multiply them together and get 96.8, but we don't get bits of teenagers, do we? And that's open to discussion. So we now want to go from a continuum to discrete values. So we always go to the lower value. Okay. Right. Okay, so we're going to go down to 96. So you can't go up to 97. And I don't like that word, definitely. I would change that to probably. Okay. Right. So I'm going to say that that should be probably. But don't let that distract from the problem. Right. So the issue here was to identify the region of interest. Go to the table, get that value, and then figure out how we're going to get the probability of interest. Then we brought it back in here, and that probability is a fraction of the total, a fraction of that 1000 there. And then we just summed it up at the end. Right. Remember, you can always rewind here. Always rewind. Or turn off. Right. Let's stay with this here. And let's look at probability of teams with heights between 1.6 and 1.75 meters. Okay, so here, the mean standard deviation are going to stay the same. They're staying the same, 1.7 and 0.1. So I think we need to bring back the normal curve or the bell curve to get an illustration where x values are 1.6 and 1.75 for us here, and the total of teenagers, they're going to stay the same. Okay, there's my mean 1.7, 1.6 to the left, 1.75 to the right. So we're looking either side of the mean here because we are looking between, okay, between those two values. So what I've got here is two probabilities of interest. P1, that's between 1.7 and 1.75, and P2, it's between 1.6 and the mean 1.7. So it looks like it's a combination of P1 and P2 we're looking for here. Okay, so that'll be our combined area. Okay, like we said, x1 is 1.6, x2 is 1.75. So let's go and get our z values. There's our little formula for our z scores. So we're going to calculate both of them. On the right hand side, I've got mean standard deviation, my two x values. So I might as well calculate them at the same time here. Okay, and that's what I'm going to be doing. Yes, so for x1, 1.6, put that in there and take out the top. And what we see here, z1 comes out as a negative value. But our table for the z scores, they don't involve negatives. That's not a problem. We just make it positive here. That's all we're going to do. And we'll use the symmetry of the curve itself, and it will not be a problem. You'll see once we go back to the graph. Right, okay, we've got Z1 there, positive 1, okay? Because our table only deals with 0 and positive values. Let's get Z2. Let's pop it in, tidy it up, it comes up positive, that's fine. That's fine, but we've got two Z values here, so let's go and get the table. So Z1 is positive 1, Z2 is positive 0.5. Okay, that's what we're saying here. So there's our standardized mean is 0, and we're going to go from 0.1 down to -1, and those are the values that we're going to use, apart from it's going to be positive 1, and like you say, they're the wee keys that they unlock the areas which are probabilities here. It looks as if I'm going to be adding together P1 and P2 because I'm coming away from the mean on both sides to get the combined probability. Right, okay, so I'm looking at 0.5 and 1.0 here. So there's 0.5, and because it's exactly 0.5, I just need to come down from Z here on the 0.00, and it looks like that's 0.1915, okay? And I then need to come down below Z and go to exactly 1.0, okay? But I've already highlighted the column there, you can see it, so I'm just going to go down there. I've just slotted in P1, go down to there, and it looks like the intersection between row and column there, it looks like it's 0.3413. I'm going to go for that. So I've got P1 is 0.195, I've got P2 is 0.3413. Then just going back to my bell curve. I just want to see the associated areas probabilities. There's P1 and P2. So my total probability, PT, is just the sum of P1 and P2. Add them together, and there's our combined probability area of 0.5328. So let's go back to the problem. And so we're looking at heights between 1.6 and 1.75 meters. And since the graph actually gave us that exactly, okay, that's the probability that we've actually found. Okay. So remember, we're talking about teenagers here. So that probability, we're going to use that in conjunction with how many we had. So it's going to be that probability times the actual total number of students, which is 1,000. So we put that in the calculator. It comes out with 532.8. And we've seen previously that we have to round down to the nearest whole number, the nearest whole teenager. So for us here, we can see that the probability of students having a height between 1.6 and 1.75 meters is 532. And again, I'll change that definitely to probably. So hopefully, I looked at two ways we could go and get a probability from the table. That first one there, because our probability was in something called a tail end, we had to subtract our probability from tail from a half to give us a desired probability. But in this example here, we were looking at probabilities either the side or the mean. So we just had to go and get our z-scores. As long as they were positive, just go from the table, add them together, and then using the overall probability as a fraction of our total, and then just round down here. So again, probably 532 between 1.6 and 1.75. And I think that's us finished there. Well, I know that's us finished there because we've run out of pages. So like I keep saying, if in doubt, just go back and have a little listen, and also go back and look at the exercises that look in particular about explanation and how to locate the regions of interest. And those regions of interest under the bell curve are your probabilities of interest. So I'm going to finish that there. That was the normal distribution probability video 2. Right, so I hope this helps in some way. Okay, folks, I'm going to leave it there. So bye for now.